Hey, hello everyone. How is it going? Good. What about the party yesterday? Did you stay long? Nice, that's a good feeling. I was about to stay long and after I was like, nah, maybe I need to work on my slide a bit more and maybe I should have stayed longer, so we'll see. Okay, so as you have seen, this title of my talk is about TensorFlow and I kind of like had a bit of like hard time to see how deep we are in a topic. So if you can put your hands up, how many of you do some machine learning, like, I don't know, from time to time? Whoa, that's amazing. Okay, how many of you did some neural networks? Nice. And deep learning? Cool. And TensorFlow? I like it, people. Okay. So since, depending on the city, sometimes background is like a bit harder, right? For instance, in Munich, I also organize machine learning meetup when we have like a bunch of talks about, I don't know, all kind of deep learning, right? And sometimes that a city is like a bit more prepared, so like a general audience is like a bit aware of things. Here I wanted to kind of start with the small things and after go like deeper and more high level. So hopefully even if you, I don't know, Android developer or like web developer, you're not going to be feeling lost. It's more like we will get there. So we will start slowly and after get somewhere else. As you also noticed, those slides don't look like super amazing. Like for instance, like picture is like super small. You know why? Because it's in Jupyter and there is a real JS that rendering that. That also means that all of the code that they're going to be showing today, and there's going to be a bunch of it, you can just download Jupyter Notebook and just like run through it. So it's kind of an excuse for myself, like why it doesn't look that amazing. Yes. One of the parts as well that people start talking like all this machine learning stuff, right? And it's all amazing, right? Google changed from mobile first to AI first, and sometimes it feels like hype, right? And I didn't want to bring like many examples like how you can do like image classification is in this part. So since we are talking about Hitchhiker Guide to the Galaxy, I brought this like Babelfish. Like who is aware of what is that? Yes, at least a couple of people traveled the galaxy. So in the original movie, right, they had this small Babelfish, right, that one of the actors kind of like putting inside of the ear, right, and this fish is translating to no matter what language you are listening to, right, into your own language, basically, right. So it sounds pretty cool, right? You don't need to learn a language. You can go to whatever country, and it just like does it for you. Turns out it's not like futuristic and super crazy. If you have seen, announcement event from Google, I don't know, maybe a couple of weeks ago, they also announced like Google Pixel Buds, right? So those like headphones that you can tap on them and they're going to be doing translation, right? And it's kind of like pretty close what Babelfish basically does, right? But you can basically buy it more or less right now and it's already going to be working. What is interesting about that I don't know, I think like a huge percentage of that is basically based on the machine learning and deep learning, right? On this case, on this picture, you can see just like a nice animation how Google does one-shot learning, right? So they do they have a corpus like of different languages, right? And essentially they are able to, build embeddings. That means that, you can you have different words, right? And based like how words are used, right, there is some common sense, what they call the distributed presentations, right? And based on this information, if you give your network like a huge amount of text, right, you can learn that, I don't know, stage is somehow similar to the speaker, right, or close in the embedding space. And what they also using like for translation, like as a part of it, right? On the other hand, like right now, even, generating this audio waves is also in many cases like way better if you use like deep learning there. So there was like an article from Apple and this one from DeepMind, and they basically switch it more or less completely, right? And sounds of what Google Home saying, what is other part of Google is saying, and most likely this Google Buds, they sounds also like way better, like way realistic, right? Because you don't do concatenation of like smaller pieces, but the network does this like end-to-end basically. It's a WaveNet, yes. And when we're starting to talk about all this, I don't know, like machine learning and deep learning stuff, usually you see this picture. Like how many of you have seen that? Yeah, it's quite many, especially at Google I/O and other places. And it's cool. Like it's showing you some information. There are some layers, right? And I don't know, like kind of a structure, right? And it's magically kind of works, right? But the problem, right, is that sometimes it's kind of like missing all the details, right? You're like, okay, I got data, I put it inside, pam, pam, and it already works, right? It always reminds me of this like OWL, how you do that. You do circles, pam, pam, and here we go, like here's already OWL. And what is even more funny, and like the same time is like helpful, right? That many people that I was like meeting like lately, right, they were like, so what do you do? I do some, I don't know, data science, machine learning. They were like, oh yeah, I can do data science and machine learning. Like, I did a course like on Udacity, you put data inside, bam, bam, and it already works, right? And I mean, on one hand, it's fine, right? Because people feel motivated. On the other hand, like, it's not that easy, right? Otherwise, we're not going to get paid for that. And I wanted to go like a bit more in details, right? But is it going to be like all this crazy about formulas? And by the way, this is a formula, I think it was for GANs, right? How you can do that. No, like, I think it doesn't make sense, right? Because, I mean, we don't have like time for that, and maybe, you know, you need like more your own time to digest it and like feel good about that. So we kind of like have like a different approach. We kind of go through a bunch of like code samples, trying to, you know, like show some pain points, and from there explain, okay, why did we do that, or like what was happening there. Yeah, and some first part is basically it's just how we do kind of logistic regression, just to give you a feeling like what is that about, and after we will, you know, go like deeper a bit. Yes. If any moment you feel like what's happening, just put your hands up, and I will react on that, and I don't know, we will slow down or maybe do something crazy. Okay, so I think if you were doing, I don't know, computer science or other related subjects, most likely you have heard about logistic regression, right? And you know already how is it working, and like have some ideas. It's a very basic and super simplified approach that you have some nice kitten, right? Because everybody loves them, and you have some you know, vectors that you transfer it afterwards, right? And theoretically, you can, you know, learn some kind of like representation that will be able to, you know, have some activations or like hot points like on the pictures that will say, okay, because I'm getting, you know, positive values here, right, and negative like somewhere else, right, I can basically detect that it looks like cat, like in that direction, right? And because we don't want to do it super simple, we can also add some nonlinearity, right, that in future we can use it for something more complicated, right? And I mean, there's like a bunch of formulas how you can, you know, in terms of like mathematics, define it, right? And yeah, so you can define your functions that is based on your weights, right? Your input vector as some bias. You can add some activation on top of it, and you can have some loss function, right? So you can understand how bad you are, right? And on top of it, you can have like a cost function that you're trying to minimize, right? Next one. Yeah, but you know, if you have this part, you still need to learn like what weights are coming from, right? And I'm not really going like that much deep in details because I think it might be like a good topic to talk about, but you can also like easily Google how exactly backpropagation works. But ideas that you know, you have the way how you compute your cost function, right? And you can understand how to take like derivative of that, so you know, okay, what smaller pieces you're taking from there. And if you will have like a small implementation in, I don't know, like a NumPy, for instance, it's not going to be like super complicated, right, in that direction. So the formulas that you have seen before, like it just goes like in the presentation of NumPy, right? And once you analytically compute like derivatives, you can also like measure how much they coming from, right? And when you do like in direction of optimization, right, what you do is basically you compute your gradients, right? You know that, okay, you have some learning rate, how much we kind of like going deeper, and like how fast we are. But overall, it's about, you know, step by step trying to adjust like your weights and like biases in that direction. And I mean, okay, it's not that hard, right? You can also, you got this working, you got like your weights, and after you basically compute the same functions that you had even before, right? And yeah. Sounds good in that direction, right? And I mean, I'm not focusing that much on those slides because they're still going to be like available online, and I better spend a bit more time like with TensorFlow. It's just like to show you out that, you know, it's not like totally crazy. Yeah, and essentially your model is basically what it does, like it initializes those like weights and biases, right? You do some optimization steps that we showed before, and when it's get like into proximity of your good parameters, you say like, okay, we get from there. You know, it's kind of like taking some time and depending like on structure, because we had just logistic regression, right? It's pretty straightforward. But if you go to like a deeper, like I don't know, you could do like a multi-layer perceptron even, it's getting more complicated because you still need to do some gradient checking, like other techniques that help you to understand that your implementation is still working, right? And I mean, especially right now, there's like a bunch of companies that do all those like frameworks for neural networks. And I mean, sometimes I have a feeling that you know, everybody wants to invent their own, right? There's like Amazon, there's Google, there's Facebook with Cafe 2 and stuff like that. But today we're going to be talking more about TensorFlow, right? So TensorFlow is kind of like a big animal, right? It has many things that are not really super visible for us. Like for instance, all those super useful but not super, you know, applicable by like big percentage of people is execution engine, right? That knows like, okay, how do I work like with your symbolic graphs? Like how do I schedule them? How, well, like what to do with that, right? And plus some like optimizations as well that can run your vector operations like even faster on all kind of hardware, right? So you don't need to think like, okay, I implemented it like in NumPy, now I need to use like, I think it's called like SciPy. There's a Python package that you can, not like SciPy, but CuPy, that can run it like on a CUDA architecture, but in this case, TensorFlow is kind of like taking care of all those things. And even if it's like TPU, you don't need to like, you know, implement the stuff like on your own. On top of it, there is like a front end, right? Like that gives you ability to write some Python stuff. And even on top of it, there is also like layers that give some, you know, structures that you don't need to re-implement it. Lately, they also release like data sets that help you to, you know, like, since you already have GPUs, right, for like fast learning, but in many cases, like pre-processing the data is like getting like a bottleneck, and they trying to build like a good wraparound that to make it even faster. And on top of it, there is like a Keras that is also going to cover in the talks that gives like even higher level of abstraction there. And what is kind of relatively new is like Kent estimators. If you use sklearnkit or scikit-learn, it's kind of in a very similar format. You can just create like DNN and say fit, and it's like kind of magically works. So theoretically, you can also use that, but practically, it feels like more that, you know, you're working on that. If you like defining something like customized and architecture-wise, is also more helpful. If you give like a bit of concepts introduction, right? So there is like TensorFlow as a word, right? Like it has like two different parts. Like one is like tensor and another one is flow, right? Quite obvious, obviously. But so if you're talking about tensors, right? Those like two different pieces, right? In mathematics, there is a different definition of tensors, but in TensorFlow world, is basically you can define you know, different ways of, I don't know, in this case like constant, right? But multiplication is also going to be like a part of this operation, or like in this case, if you print it, right? First is going to be tensor. Oh, sorry. But the result is also tensor, right? So you can define your graph basically in those like tensors. What is also interesting, right, that, you know, if you do like this multiplication here and we print result, and then of the day, it doesn't really show us result, right? Like, why is it happening? Because all the concepts that, you know, TensorFlow and this like scheduling engine, it does it later, so it's like lazy evaluation, and you know, like it still can do some crazy stuff like how to optimize it, because I mean, for this case, there is nothing to optimize, but in general case, there is something more advanced for that, if you have like deep network. But what is kind of essential for that, once you have TensorFlow session, right, you can say, okay, there's a, you know, this operations that, or tensors that I would like to execute, right, and when you do session run, it's kind of, okay, does some scheduling, some magic in the background, and only after it does evaluation and execution of this lazy formulas that you had, right? And what you can do is basically, it's kind of like a hacky way and not super visible right now, but wait a second. So once you define it like in the current scope of your script or Jupyter notebook, right, you can also, with with a TensorBoard, you can try to visualize it. And since this one is like slide embedding not really good, we have this one that basically shows that for the operations that we were showing, right, it's going to have like graph like that, right? And if you were surprised that this like multiplication doesn't look very comfortable for you, you can still use like a different sign, like depending like on what kind of multiplication you have. Yeah, but basically you have session basically based on what backend you're using and like where to execute those things. Yes. What is kind of essential for that is also being able to, pass some variables. So like in this case, we are saying that, okay, I'm creating like a placeholder, right, for X with, some information that I'm going to be using afterwards. And you can afterwards pass it inside of your session. So that's how you're also going to be like learning your models. If we like go in direction of initializing parameters, right? Because it's what we usually do in the beginning. It's where TensorFlow is kind of like getting verbose, right? Because every time when I'm defining like a variable for my weights, right? And it's not like how you would do in production system, but it's more like a visible, like what's happening there, right? And when you're defining that, you will also say, okay, like what is the shape of this part, right? And in many cases, like you need to sit and like understand what you're going to be doing there, but there's like some complexity with this part that's happening, and I will mention it like a bit later, like why is it important. And there's also like some fancy way like how you can do like proper initialization, like with Javier initialization, for instance, and stuff like that. But what I would like you to just like see that we initialize in parameters, and you need to know like shapes of the layers what you're going to be using, right? And when we were talking about, there's like a loss function, like, and how we evaluate all those things, right? Before we were like implementing like our own, right? And depending like, is it what kind of classification? Is it like multi-label, right? You still need to do like your own jobs there, right? With that case, like, because TensorFlow is already like a framework, right? They already have all things like in place. And it's also kind of like just going like a bit ahead. Sometimes in Keras, you like missing some parts that what they call like, or like in Keras is like a low level, but even for multi-level classification, we have some issues that we need to like implement stuff. But back to this part, so you can basically just use cross entropy with logits. And in your code is basically going to be pretty straightforward, right? You're getting your labels, your logits, and after you can just pass it like as a const function. So it doesn't really go like super crazy, right? We still, like in original part with logistic regression, we had some forward propagation, and that's basically what we have here, right? We have like a separate, the part that has like our parameters, right, that we want to pass on, like if you do like inside of the batch. But basically, what you do is pretty similar what you did like in NumPy beforehand, right? Just like it's different prefix. And they already have like all kind of like activations like relu or leaky relu that kind of like a part of the story for you. If you feel like that, you don't really know like what directions we should be, like is it relu like or sigmoid or why we're talking about those things, just like catch me afterwards and we can have like a long discussion like how I don't know, things are helpful like for gradient vanishing like an explosion like afterwards. But I'm afraid that here on the stage it just like take it as a given, and after you can always go deeper and see like why, I don't know, I'm using relu and not like proper sigmoid here, but I wouldn't go like that much in details. Yes, and after, if you like defining kind of the model like in TensorFlow way, right? Besides like having the boilerplate that we kind of do some reshaping part, right? We have like a placeholder like parameters that we showed before, right? But essentially it's pretty similar, right? You have like a forward propagation. What you did before, right? You were like analytically computing like your gradient, right? And after trying to like implement it, what TensorFlow gives you is they have like a set of like optimizers, right? That depending like, okay, is it going to be gradient descent or stochastic gradient descent or the one with momentum, right? Just like to, for those of you who are not familiar with that, just depending like how you have a function that you're trying to find, I don't know, like maximum or minimum, basically what you're optimizing for. There is like a different numerical way to do that, and there are like a different behavioral of those things, right? So for instance, like Adam might do some adaptive stuff that is more sophisticated than just using like stochastic gradient descent. But as somebody who just want to play around with that, you just can, like use like Adam optimizer as like one of the default ones and just get it from there. And what you can do afterwards is, okay, you're providing like a learning rate, and you can say like minimize my cost that defined beforehand, right? And even if you remember, like cost function was not that complicated to define, right? So it's just like a sigmoid cross entropy. Right now it's like a bit complicated, but after we will like switch into Keras when it's going to be like way simpler. Just like to show you also like a part of complexity. Yeah, and what you do afterwards, you have your sessions that you are running, right? Here we kind of like do some like mini batch part, but basic idea is that you have like a session that you're running with your optimizer and like cost, right? And yeah, essentially it just if you run this model, it's going to be showing like, okay, like after every epoch and how is your losses basically changing. So it goes pretty fast, pretty good, right? And again, I'm going to share Jupyter Notebook afterwards, so you can like click those things and try to change the parameters and make them available. Yes. Okay, so we can write those things, right? But one of the problems why the things was not taking off is like neural networks, right? I mean, there are like multiple theoretical things, right, that we were not able to train them deep enough, right? But another problem, resources, right? I remember like back in, I don't know, 2007, I believe, like when we were like using some neural networks for like as a kind of a student project thing for, I think like detecting some faces and like classifying like other things, right? We had like a separate machine that was running like for quite some days, and it was like training on like on its own, right? And it was like machine with CPU, right? So it's like going to be like super slow. But the problem is that as human individuals, right, or like your personal project, hobby one, it's like takes some time, right, to train those things. Hopefully for us, like there are like a bunch of cool companies that invest in like a good amount of resources that make it available, and they also working like on building like a cool architecture. So like in this case, it's an Inception model from Google, and you can like download already pre-trained models, like using like, okay, it's a pre-trained for some cases, right? But turns out that if you have those like a deep layers, right? After having like a bunch of, you have like a bunch of classes, right? And in this case, I think they use like, in some cases like it's ImageNet, like data set with like 100,000 of images. Google has their own data set, but basically they learning, to understand, like to classify different classes, right? And meanwhile, network also learns different representations, right? So if before you were coming from computer vision background and you're going to use like SIFT or SURF feature descriptors, right? Now you can just use one of those like networks and get, depending like what like level of presentation already for you, and you can do like crazy stuff that I will show in a second. And I mean, there are like a bunch of like a different network architectures, and they're already pre-trained. One of more famous one is like GDG 16, and it's like also super old. What I want to show like on this graph is basically, especially if you want to port it like for mobile or like some low-level hardware, and if you want to, I don't know, optimize for inference, you will see that, like on one axis you will see like number of operations, so like how much time it takes, and also resources, and another one like accuracy, right? And turns out not the most, like number of operations are getting like the highest accuracy, right? So sometimes you can pick up like as Inception with trees that relatively, or like ResNet from Microsoft, that like in terms of operations is like pretty low, right? But in terms of accuracy is pretty high. So just like keep in mind that you know, there is like a good comparisons of things, and I mean, VGG16 is cool, but there's like other pre-trained network that you can be using. And there's also like a nice paper on archive, basically, that you can read on those things. Yes. Okay, so imagine that Google trains this network for you, right? Can we make it easier and like use it for something from us, right? So in many cases, they sharing their models like in a protobuffer definition, and you can just like load it as we do like in this case, right? So you can define like a graph definition, and you can like read a file, but basically, essentially, yeah, if you load it, again, like it's a tensor board visualization that shows you how simplified it looks. Like if you click on those blocks, they're actually going to be extending, so it's going to be as original image inception model. But basically, you get the thing is running, right? So we got the model, right? Like, and what we can do afterwards is just basically if you know, like you define your network, right, usually you will have, okay, just like different layers, right? If you're familiar with this topic, there is some convolution layers that also take into account not only value of the point, right, but also, you know, proximity. So you basically have like a bigger high-level features. But usually if it's, you know, like multiple classes and then of the day, you're going to use like softmax, right, as a like last layer. And what's happening here, right, that before softmax, you're going to have some, I don't know, fully connected layer just to like learn some things there, and maybe some pooling like on top of it. And what you can do is basically use this information like as a feature descriptor, right? And in this case, like I'm taking, I don't know, I think like one of these intro pictures actually, and passing like inside, and I will get like a vector of I think like 2048 or something, if I'm not wrong. But basically this bunch of digits here is going to be like a really good feature descriptor for you. So you can easily implement, you know, like if you again like go to TensorBoard and you show some, I think in this case it's like PCA, but you can also do like a Disney. It's just like a way how you can put like a multi-dimensional data like in 3 dimension in this case. But basically you will see that, you know, images that kind of look alike, right, will have like a similar image vectors, right? So you can easily implement image similarity without, I don't know, spending much time. So I've been at this like hackathon in Zurich like months ago, right, and we had like one of projects that we wanted to add like image similarity, and it took us, like there was like one girl who was doing, I think like data science at Yandex, and she was like, I'm going to be using like surf and sift, and I was like, okay, and meanwhile I will try to use some feature description from Inception. And it was like way faster on my side because, you know, like with all this like OpenCV stuff that takes some time, it didn't really help that much. Yeah, and if you go like more in production direction with all this like image similarity, there's a library called like Annoy, like very nice name, but it's basically built by Spotify, and they do like approximate nearest neighbor. Oh yeah, like that's how they call library. But the basic idea is that once you have those, you know, feature representations of your images, right, you can have some approximate like neighborhoods, right, and it's super fast basically to say like, okay, I have this image that like belongs somewhere here, right, give me like a neighborhood of images that look alike, right, so you don't need to do like some KNN, but you can just like extract it from this index. So if you do it in production, it's like super cool project. Although there are like a couple of tricks, so if you're going to be using it, just like ask me, or I don't know, like ping me, I will tell you that. Yeah, so you know, you have seen that it's getting easier, right? You don't need to implement stuff, but it's still pretty verbose, right? There's like much things happening. Fortunately for us, yeah, there was like this library Keras, right? And they make it even better. So they like wrap up things like together, and they also like add some you know, like proper way to like handle, you know, the ways that you need to things that you need to implement TensorFlow on your own. But basically, if you're building like a simple model, it's as simple as it is, right? You have like a layers, yeah, that like could be convolutions, like, or max pooling, or whatever else. Like you can, you know, I can tell you afterwards. But basically, what you have afterwards, you have a model, and you're adding like all the layers like in between. So you don't need to think like, okay, what is a shape of the layer before? Like, how do I connect them together? It's like you're focusing on like more important parts than just like thinking about shapes. So it's pretty good, right? And yeah, you can also do like a pretty scikit-learn approach of model fit with like all your data, and it's pretty good. Yeah, and after, if you want to go more in details, you can also do like a model summary that shows you, okay, what layers you are having, like number of parameters. If you want to like decrease number of parameters because you want to, I don't know, move to like smaller device and you want to replace some fully connected layers with convolutions and stuff like that. Yeah, and if you do like evaluation, it's basically also pretty simple afterwards, right? What you can do afterwards is also like saving this stuff. So like once you train it, you can get it yet in different format for Keras here. But basically, yeah, it will generate you like one is like a graph definition, and another one weights basically that you can easily load afterwards. Yeah, and it's like a way how you can load the stuff. And there was examples that I trained like on NIST data set, and yeah, it was like at the end of the day, if you yeah, you have like original image, and you can yeah, model predict that gets your like image, and you can reshape to the proper shape. But basically, it will show you that okay, it's like 4 basically class that has it, so it's basically look like 4. Yeah, and if it was not simple, right, you can make it even simpler. So like Keras in this case, they have already like applications, and like in this case it's exception with 3, right? And from there you can just define it, and like you can say like weights are coming from ImageNet, right? And yeah, and you can have like a graph already like working here, right? And yeah, if you have the graph and you can load it, you can just use a prediction from there. And those examples that we had with image, and depending like on classes that ImageNet already having, it's gonna be good. But what you can do is basically freeze like entire architecture besides the last layer, and it will like retrain not entire network because it can screw up the weights, but only like your parts that it using like a feature representations and like mapping a feature representation to your own classes. You can go like even as far as using like one-shot learning, as like having like very few images that you can train on top of it. Yes. And it's already given like a pretty good idea that if you really want to use it, you don't need to like know all the details. It's like a similar direction of as I was saying, if you want to drive a car, right, you don't need to know how exactly your engine works, right? You can just be like steering the wheel and like making it working. And it's basically what's happening with like many deep learning models, right? If you know like a couple of concepts, right, how you get like image features, right, you can always like build on top of it. So it's kind of a Lego game, right? And one of examples is like image captioning. I didn't really bring the code inside, but I can share with you if you're interested. But the idea there is that you also have image, right? You have like some convolutional parts that might be based like, or I don't know, like one of well-known networks, right? And after you do some like RNN part, right, that can also map the part of the words that you are saying, right? And if you have like once a data set, right, you can say, okay, this image as a data set has some descriptions that, I don't know, like this like fly or bird is fly. And after network, you will learn it, right? So it's pretty good. And you can go like that crazy as, like even combining like more advanced, right? You get in like questions that, goes through some LSTM, right? Yeah, and after you have the same like feature descriptors, and after if you don't use like sequential model, but basically functional approach for Keras, you can just join it in the same model. So it's more about data that you are having, but your tool set is basically staying the same. Yeah, and in terms of deployment, since it was pretty fast, and I think like many of you is like, what's happening? I need to check Jupyter afterwards. There's like many ways to do that, right? Like one is a way is your own kind of way, and you have like TensorFlow serving that optimize for, you have your model and kind of run it like in the background, and it has, you can use like NVIDIA Docker and some Kubernetes that you already most likely see when talk about that, but basically you will have your own infrastructure like on GPUs that shows those things, yeah. And for Android people of you, and even Android things of you, there is also like a version of TensorFlow, right, that you can train on your like a separate cluster, for instance, and after just save the weights. But essentially, what you would do is you have like a gradient dependency, right, and you will, basically define like Yes, it's the part like where your protobuffer model is sliced, right? So you can put it into your resources and oops. Yeah. You can also define where you're feeding it. So like all those network architecture, right? They have like a specific names, right? So you can say, okay, feed it in direction of like input, right? And give me results like of output, right? In this case, we don't really use like a feature presentation, but we use it like original classes. And yeah, and it will get you pretty much working. Yeah, in this case, you can run the same one for Android or like a small Android Things device. The only thing that I also do not cover here is like how to optimize it, right? Because if you optimize for inference on mobile phones, there's like a bunch of like other steps it might be doing, like reducing like like how many bits you are storing like per weights, right? Because sometimes it's like representation is pretty high. Sometimes you can also be more efficient on archiving those models, so you can easily like decrease the weight of the models that you're saving like by a factor of like 20, I believe. So if you like interested about this part, ping me on Twitter. Like I should have like a slide from Munich when I was talking about doing deployments like for Android. But overall, it's basically it's pretty straightforward. So what I wanted basically to say here is, there are like many different pieces, right? You can go like pretty low level. You can go like pretty high level, right? But it's like your own choice, right? If you want, you can go pretty high level with Keras, with some pre-trained models, and get results like in a matter of hours. So don't be afraid of like trying that, and you can always go deeper, right? Don't be like scared of that. Okay, I need to do like all those like derivatives, like partial derivatives, and know like bunch of mathematics. It's not that much of rocket science. Like you can always go on that level, but for the beginning you can just do like clicky stuff like combining models, and it still looks pretty cool like if it's really working for you. So yeah, like there was lots of pieces kind of missing, and it's like was pretty fast, but I hope it kind of like give you like a roadmap, right? And like a guide basically, right? What things are there, and if you have particular questions on like similar topics, just like catch me up, and we can talk about all cool GANs like for 1 megapixel and stuff like that. Yeah, with that I finish my talk, please. Thank you.